Okay, let's start. So everyone can see my notebook and iPad notes, right? Okay, sure. So let me start. In this tutorial, I will introduce how to use BERT. Um, and let's look at this part first. Look at this note. This is BERT. So BERT is architecture for language modeling, and in BERT, we pre-trained a BERT model, the language model, with two tasks. First is the mask language model. Second is the next sentence prediction. And BERT stands for bidirectional encoder representation from transformers. You look at this first picture. The bird is, where's my pen? Hold a second. Okay, and look at this first one. In bird, we take the encoding layer and few transformer encoder layer. And we will get some representations. And I hope you remember what is a transformer encoder. In transformer, we have encoder and decoder. And in BERT, we only use encoder. So each is blue circle are the transformer encoder. And let's see how did the BERT trained. So if we want to pre-train a language model in BERT architecture, we should give two sentences, sentence A and sentence B. And we will randomly mask some tokens. And each sentence will split by a separate token. So here we give an input, then the BERT will predict the mask token first. So for example, here is 1, 2, 3, 4. This 4 will predict the mask token. And the BERT will also predict the next sentence prediction task. So the BERT will identify whether the A and B is context sentence. Okay, this is basic idea of BERT. And then we will use this pre-trained model after pre-training. After this model, this is pre-training. After pre-training, we will use BERT to fine-tune on some downstream task. So in this tutorial, we will use the classification task. So basically, what we will do, we will take the pre-trained BERT, then add a untrained linear layer on top of BERT, then train a new model with our classification task end to end. And this is architecture we use to fine-tune BERT on classification. Classification task. Okay, so those parts are pre-trained BERT. It's pre-trained. And here, we will get a lot of representations. Each token will have one representation. Then we add a linear layer on top of it, and this is a linear layer. And the linear layer will give us a prediction probability. So basically, we will use this probability loss to backpropagate. We will backpropagate all the layer, not only the linear, but also all the BERT layer. Okay, so let's move on to to implement the BERT model, first, here I'm on COLX, so I should connect to my Google Drive. Then I will import some packages here. And then same thing, we find the device, then set the seed. Then because in COLX, the transformer library doesn't install, so we should manually install it here. So use this command to run it, then get this transformer library. After that, we import the library, and then let's look at this part. So the BERT, the transformers, this library has 10 plus transformer-based deep learning architecture. And you can see some of them are BERT, OpenIGBT, GPT-2, Transform XL, XLNet, and Robota, and Distill BERT. So there are a lot of different type of architecture based on transformer architecture. So now we only focus on the BERT, but if you are interested in any one of these, you can go to the website to check the document. And so let's look at the BERT architecture. So in BERT architecture, they provide a lot of class for fine-tuning and also for pre-training. So here, they're the class. You can use this to do the mask language modeling. And here you can use this class to do the sequence classification and question answering. So in this tutorial, I will use this dataset. We already used it before. This is the HappyDB dataset that we are focused on the sociality classification. And because for BERT, the import data is different. So we can't directly use the torch text to process our data. So I create a function to help you create the data. Let's look at this part first. So first, we will use the BERT tokenizer from the pre-trained. So this one will help us load the vocabulary from the pre-trained model. This is a function. In this function, you should give some argument. First argument is a string. The string could be the shortcut name or the path to the directory containing the model vocabulary file. And the file name is this one. And here, in the transformer, they provide a lot of checkpoint. And this checkpoint, they give some predefined shortcut name. And you can go to the website, check. They provide a lot of different model, and you can find the one you want to use. And here, we use this one, BERT large uncased. So BERT large uncased is a shortcut. It's already defined in the list. And this model refers to the BERT model, which has 24 layers. And each unit has 1024 dimension. This is hidden dimension. And each layer you has the multi-head attention, right? Each layer has multi-head attention, and in this multi-head attention, you have 16 heads. And the total parameter of this model is 340 million. And for this uncased means in this model, we lowercase all the characters. We don't care about the uppercase or lowercase, we lowercase all. And here they use a bipair encoding. So I already provide a bipair tutorial. So you can read the bipair tutorial. You can post a question. Okay. So in bipair tutorial, I give you a video, so you can go to watch a video and ask me question, and I will not cover it in this tutorial. So the bipair encoding will help us to handle the out of vocabulary problem. So the bipair give you some subword, and in BERT, they also use a bipair encoding to build the vocabulary. And the vocabulary size is 30,000-ish. It's the word pieces. So if you want to understand what a word piece is, you should go to the bipair. So, and here we call the function. We use the function here. First, give the first argument, which is this one, the model name. Second one is lowercase because it's uncased model, so we should lowercase all the input. Any questions so far? Any question here? Okay, so because we give this a name, it's identifier. It's identifier of the transformer. So the model will download this tokenizer, download this vocabulary, and load this vocabulary to the tokenizer. Okay, so here is the downloading. Then after download, it's load to the tokenizer. Then the tokenizer will have the vocabulary. Then the BERT tokenizer will do the tokenization. Okay, so let's move to this part. Then I said I define a function to preprocess the data. For the preprocess, I should give three argument. So argument here first is directory, the directory to my train set, then the label dictionary, label to index dictionary, and the BERT tokenizer. Oh yeah, I should say this one. So this is the label to index dictionary. So we just map the label, the text label to the number, to the number, because that's system. We should use the number in our system, right? So we map no to 0, yes to 1. Okay, let's go to this function. So this function, we said we give the path, give the dictionary, map dictionary, and the tokenizer. And you have some optional parameters like the max length. So the max length of your input sequence and the mode. So for this one, we will set as train by default. And what's the difference between train mode and predict mode? Because in prediction, we don't have label, so we can't load a label in prediction process. So let's go to train. So in train, we will first use the this one. This is pandas function to load the CSV file. Then send this CSV file to a data frame. You should give the file path, and it's split by tab. It's CSV file, so we set this to tab. Then the head. The first row is the header name, right? So we set the header name head equal to 0, then I will change the name. It's help us to handle all different situation. And here I use the attribute of this data frame. This attribute is label, which is this one. To load a label, then convert the label text to index. Then we get the label. And after, if I will do this part, it loads the content. So load the actual text. When we load the text, we should add some special token. As I mentioned, so BERT requires a classification token at the front, in the front of the text. So you should add this token before all the content. And then we use the tokenizer to tokenize this content. We use this is a BERT tokenizer, we predefine it. And here, I use the max length to truncate the longer sequence. And because we add this special token, so I will add 1 to avoid trunk a lot. And here we add a split token. So because in pre-training, the BERT has the split token. So we should mimic the pre-trained behavior of BERT. So we should add the split token. So the truncate in this part. So this truncate is very straightforward. For example, here we have a list. Let me give you a list. Okay, this is a list. So we set the max length equal to 3. So in this process, first we will add CLS at the beginning, right? CLS. So when I truncate it, I will just select the first 4 items, use this truncate range, right? So 1, 2, 3, 4. Then this part will be removed. This is truncate. Can you understand it? Okay, so let's move to this part. So we will append this split token at the end of the list. For example, here we add it here after truncate. Okay, so comment out. Let's go to this part. Then this tokenizer has a function. It will convert the token to index. Then you will get the index tokens, index sequence. After that, we also need to create the mask. So the mask will help, it's attention mask. So when we do the multi-header attention, we should only attention on the actual word, the word in our text. We shouldn't focus on the pad because we will pad the sequence, right? I hope you already know what is pad. So pad will give us a fixed length because for different sentence, the length is different. So we want to get the fixed length sequence. So we use the pad. But when we do the attention, we should only focus on the the real sentence, not the pad. So we will create this mask. In this mask, if the word is a real sentence, the mask number will be 1. But it's the pad token, the number will be 0. So when we do the multiplication, the attention function will ignore the pad tokens. So this is just for the attention. And when we generate this attention mask, we will convert the input sequence and the mask sequence to tensor and return the input, label, and mask. Any questions so far about this part? Okay, no question about this data prepare. Okay, so let's go to here. It's a small clean, clear to tell me what's the output. So first, we have a tokenizer. The tokenizer will tokenize the input. So this is the input single or pair of them. Here we are using the single sentence. This is we're doing the text classification. We are not doing the pre-training. So in our task, we only have one sentence, like this single sentence. Can you understand? So you can see this example, we only give one sentence. And yes, right. So the next sentence prediction is in the pre-training. So when we do pre-training, we need the next sentence prediction. But when we fine-tune it, we don't need any pre-training task. We don't need mask language modeling. We don't need the next sentence prediction. So we only do our task, the specific task. Question? Yes, it's already pre-trained, so we don't need involve any pre-trained task. We only focus on our own task. Question? Okay, so let's see, because we only give one sentence. This is a sentence, this sentence prediction, this text prediction. So we give a sentence, then tokenize it. This is a BERT tokenizer. So you can say there are some different in this sentence. The minute split to two part. So this is bipair. This is subword. So in BERT vocabulary, if it's a whole word, it will look like the original word. But it's the subword. They will add 2 hashtag before the strings. Okay, and here, let's look at the index number of first sentence. We convert the text to the index, and we pad the index. You can say this is a pad. This is pad token. The index of pad token is 0. And after pad, we get this first example. And the same for validation set. We tokenize, then convert to index, then pad the strings to get the pad the list. We get this padded list, which length should be 34. Okay, then we will do this for all the training example and validation example. And we get this training output. The training output is 8,000 by 34. So this is the number of samples. In our training set, we have this number of samples, and this is the sequence length. This is fixed sequence length. And here, because we set the max length is 32, and we add 2 more special tokens, it will be 34. Okay, then after that, I believe you're already familiar with this one, the data loader. So the data loader will help us to save the memory. Here, in the paper, in the BERT paper, the author recommend the batch size as 16 or 32, and then we use this large one, the 32. And in the training loader, we want to generate the batch in each epoch randomly. So we use the random sampler. And here, for the validation set, when we evaluate the model performance, the order is doesn't matter. So we use a sequential sampler. Okay, any question? So let me move to this one. This is a loading pre-trained model. So in this part, we should load the model weights. Here we use the same thing, the BERT model from pre-trained. And this is a function when you use it. First, you should also give the model path. So the model path can be the shortcut, the predefined shortcut. You can find it in the list. And you can also give the directory to the real checkpoint in your directory. And here, I also set 2 other parameters. Here, I want the model return all the hidden states and all the attention weights. So I set this parameter equal to true. And because we use this shortcut name is already predefined in the transformers library. So the transformers will download the checkpoint, then load the weights to initialize our model, our BERT model. And we send this model to the device. If we have GPU, it will send to GPU. And here we go to the this part. We use the first batch as example to explore the BERT model. We generate the first batch. Then in this batch, yeah, I should go to here. Let you see what in the batch. So in this batch, we have 3 things. Here, the first one is train input. It's a sequence index, the sequence tensor. And the second one is a training mask. It's a mask sequence. And it's the attention sequence, attention mask. Third one is a training label. So all the label for the training batch. And same for validation, you have sequence input, mask, and label. So in each batch, you should have 3 inputs. And here, we use a for loop to send each element to device, the GPU device. Then we will flatten the batch. So the batch has 3 things, so we should have 3 variables. The 3 variable is this name. And let's give those things to our model. So our model won't get the input sequence, the input IDs, and the attention mask equal to the input mask. We give this 2 things. Then because we already turn on these 2 hyperparameters, these 2 parameters, so we will get 4 variables from the model. So this is 4 returns. This 4 return, first one is last hidden state, polar output, hidden states, and attention. So let's see them one by one. First one is the last hidden state. The sequence of the hidden states at the output of the last layer. And the shape of this output should be batch by sequence length by hidden size. And you can consider this as the outputs of LSTM, the first return in LSTM. It's come from the last layer. So in our BERT, the last layer is this part. You can assume as this part, the last layer is green box. Okay, and the sequence length, we have the sequence, how many sequence, and the hidden size. In the large BERT, the hidden size is 1024, this one. Okay, so let's see the second one. The second one is the last layer hidden states of the first token. What's the first token? It's a classification token, COLX token. So our this pooler output is a first token, and you can consider this output as the second output of LSTM, which is a hidden, right? It's a last hidden in LSTM, but here it's the first hidden, first token, and the size is 32 by 1024. Okay. Any question for this two? Okay, all good. So let's go to the third one. So the third one is the hidden states. It's a list. It's a list of tensor, and one for output of each layer, and add the out of embedding layer. So let's look at this first. So because it's a list, let's print out the length. The length is 25. Why is 25? Because it's big. This is a large BERT, which has 24 layers. So it's 24. And add the embedding layer, it's one layer. So it's 25. And for each one, let's extract the hidden states from each layer. We use this for loop to look at the hidden states from each layer. You will get the same hidden size, which is 32 by 34 by 1024. So it's the batch size by sequence length by the hidden size. So all the layers has a same sequence, a hidden size, which is 1024, right? And let's move to the attention. So in BERT, each encoder, you have the multi-head attention, right? So look at the iPad. You can see this is the multi-head attention part. So the multi-head attention will give us some attention weight. So the model will give us all the attention weight in this attention list. In this attention list, it's a tensor, and it's a list of a tensor, then one for each layer. And let's look at the list length is 24 here because we have 24 layers. Then let's look at each one. Each one is a tensor. Then the tensor size is batch size 32 by the number of head. Large BERT has 16 heads, so it's 16. And the sequence length by sequence length, it's 34 by 34. And I hope you remember how to do the multiplication, attention multiplication. So this is we can consider the first length is a query, and second length is key length. So the query multiply with the keys get the attention rate, right? Okay, so any question for this output? No question? Okay. So let me move to the linear part. So in our classification task, we will use a Pooler output, which is a hidden representation of COLX token. And we will use this Pooler output as a context representation and pass it to a fully connected layer. And at the fully connected layer, we will get the prediction probabilities across all the labels. And in this paper, they refers to many different methods to get the context representation from BERT output. And you can read them and you can investigate the different methods in your project. You can try them and show the result. But in this tutorial, we just use this Pooler output. And here, because our output dimension is 1024 from the BERT, why do we pass owning the Pooler output? So this is classification task, right? It's not sequence labeling or some else. So we should have one vector as the context vector, context representation to do prediction. It's same we use the last hidden to do prediction in LSTM, right? So this Pooler output is a context representation. And yeah, and I mentioned in this paper, you can use different method to build your context representation. You can see this table. They use a different layer output, different layer hidden state, and they concatenate the first 4 layer or last 4 layer, or use a min or max pooling, or concatenate all the output. So, but in the original paper, they only use the last one, the Pooler output, but you can try this different method to build the context vector. Okay, so we get our context vector, which hidden size is 1024. Okay, so in the linear layer, our input size should be the hidden size, 1024. And it's a binary classification, so the output feature size is 2. But the Pooler owning the first, no. So because it's the encoder, right? What if you, let me finish this one first. Owning the first token cell. So it's no, because it's transformer encoder. So in transformer encoder, you can see this connection. Each token will get all the bidirectional context. So all the information is available for each representation. So it's in this representation, it's already concatenate all the context representations. So this is different in transformer encoder. And it's updated across the sequence length. I'm not sure what the meaning of this one. So because no matter what length in your sequence, you can get all the context, right? For each transformer encoder, it's naturally bidirectional. So you can get all the context information. And you can get the kind of separate. Nope. So in STM, we have time step, but in transformer, we don't have time step. In transformer encoder, the transformer encoder load all the sequence at the same time. So it simultaneously get all the context. So you don't need to use the last one. And what if you if you do the poster tagging, you should get all the hidden states from last layer. So if you do the, let me use another color. If you do the poster tagging, use this one, use this one, use this one, you will get all the hidden states from last layer, then use hidden states to do prediction. E1 have the if you want to get the E1, E2, E3, you should check the hidden state, the last hidden state. So last hidden state has this, the second dimension is the sequence length, right? So the first item is CLS. The second item is token 1. The third item is token 2, the representation of token 2. So can you understand? Did I answer your question? Okay, so let's move to the classification. So when we pass the representation through the linear layer, we will get the output. The output size should be batch size by 2. And then same thing, we use the loss function. Loss function to calculate the loss. Okay, this is the first element, the first batch loss. Okay, we finish this part. So before we put everything together, any question? 1 minute for you to think about question. Okay, so let's go to the class, BERT classification class. How can we predict each token stack? So it's same thing. Let me clean this part. Okay, so now we will do the poster tagging, right? This is the green is the output. So we will get the hidden 0, hidden 1, hidden 2, and hidden 3, right? Each one is the 1024, right? Batch size by 1024. So you just add a linear layer here, then you give the first one, give you first prediction, and you give the second one, give you second prediction, and same thing. So this is also a linear layer, right? And yeah, any question? Is this clear? Linear layer for each token? No. So you don't need the linear for each token because you don't know what the token learns, right? So you just give the, because they have the same shape, so you can give them one by one or do the matrix multiplication. You can share the layer. You should share the layer. It's same layer. Could you give me a dimension of, I don't know what's the number of your label. let me assume the post tagging, the post label equal to 3, for example. So here, your input, let's assume your sequence length is 34, right? Then each one has 10 by 24 dimension, right? This is your input. And when you pass through the linear layer, your output should be sequence length by 3, which is the number of labels. And this one, the input size should be 1024. Output size should be 2. Is clear? Yeah, I just assume you have 3 type of labels. Yeah, you can. Yeah, it's so the weights of the linear layer is 1024 by 3. It's a number of weights in your linear layer. Okay, so let's put everything together. So we should build a class, right? So in the class, we have initial and forward. Initial, we give these 3 parameters. First one is our dictionary, the label to index dictionary. This will help us know how many labels in our dictionary, in our data set, and the model path, and the hidden size. You should know what the hidden size of the bird. So for large bird is 1024 here. And we instantiate this model, give it 3 parameters, then instantiate the model, then send the model to device. And then let's count how many parameters in this model. In this model, we have it's 3035 million. So I also calculate how many memories we need. So we need around 11 gigabyte memories. All right, so it's a lot of, you should be careful. If you have very small GPU, you will get out of memory error. But fortunately, I guess this now, Coda Lab gave me some large, let me see. Yeah, I get Tesla T4. This one is 16 gigabytes. So I'm good luck. I get this one. I will not get the out of memory issue. And let's see. Let's move to train the model. Okay. We should initialize some optimizer and scheduler. Here in the paper, the author recommends some hyperparameters. So for the batch size, you should use 16 or 32, and learning rate is super small because we use the pre-trained bird. So it's already pre-trained on huge data set. It's already learned a lot of common knowledge from human language. So, but we want to fine-tune this model, this pre-trained model on our specific task. But when we fine-tune it, we want to preserve the learned knowledge from pre-training. So if we use a huge, very large learning rate, the pre-trained knowledge probably will be removed. So here we use a very small learning rate to preserve the pre-trained knowledge. And because it's already pre-trained and it's already have a lot of knowledge, so the epoch will be very small. You just need a few apples to get the best performance. And here we use some complex optimizer. This comes from the transformers library. You can just use it, but we will use a warm-up in the scheduler. So the warm-up will help the model to adjust the learning rate, and the learning rate will decay during the training. And we would use this loss function. So after that, we use training. I define a training function and a validation function. In training, we should add the clip gradient norm. This helps us prevent the exploding gradient problem, because BERT is a huge and deep model. We should be careful the gradient explosion. Okay, and here we use a for loop to train the BERT model. Then we save it and see the performance. You can see after 2 epoch, you can get the validation accuracy, and this accuracy is much higher than the LSTM and CON. It's 94. Okay, so let's move to visualization. So before visualization, any question for training and some detail about BERT? Okay, so let me move to visualization. So this is attention visualization. I give a sentence. So this is scheduler. That's a long story. So I probably not give you some example here, but we can discuss later because it's already almost 3 o'clock. So let me finish it quickly. So here, I give you an example, and this is a validation sample from a validation set. And I think this sociality is yes. And this is very nice example because you can see there are some co-reference. She refers to my daughter, right? And let me see, first I give you a sentence preprocess. In this example, I will use this function to preprocess the input. The input should be a list of strings. This string is our input sentence, and we only give one string here. And rest part is same as the data prepare function. We add the start token, then tokenize it, add the split token, then convert to index, then we generate the mask, then we get the output, and we also return the tokenized text. This is output look like. Then we use this, send this input to device. Then the size is batch size by sequence length. And then we give this 2 input to BERT. BERT will return 2 elements. First is output, the prediction output. Second is attention weights. Okay, this is we already defined in our class, forward function in the class. So we will return 2 things. Here we get 2 output, and we we check the prediction result first. The model gives us some correct prediction. You can see the output is a vector which has 2 elements. First element, there are some it's a logit. So you get the logit to find which one is highest one. The second one is higher than first one, so the prediction index should be 1, and which refers to yes. So the label should be yes. And here we look at the attention weights. The attention weights is hold a second. The attention weights is a list. Length is 24. Then we get the shape of each one. Here we only visualize the last layer of the bird. So we use this trunk to get the first layer. Get the first layer in the list, a last layer in the list. -1, and because the batch size is always 1, we only give 1 sentence. So we will squeeze the first dimension, and now we get the first attention weights, which is a number of head by sequence length by sequence length. And each head can provide a matrix, which is sequence length by sequence length, and each head may focus on particular language mod information. So we want to learn, we want to inspect what knowledge the model get, the different head learned. So here we detach the tensor from GPU to CPU because our visualization were on CPU. So we should detach from GPU. And we only focus on the CIS token because you can say we use the CIS token as a context representation. So we consider the CIS token is related to the classification representation. So we focus on the hidden weights of CIS token. Then we inspect how the query CIS token attend to the key tokens in the 16 head. Then we convert the tensor to NumPy. Then get this one help us get the list, the token list, tokenize the token list. Then we use this function to visualize it. So the y-axis is the number of head. So the first head to 16 head. And the x-axis is the sequence text. So you can see the intensity reflects the weight, the value of the attention weight. So if more darker, it means higher weight. So you can see the fourth head more attends to my daughter. So you can say this probably some name or some words related to socialities. This probably can give us some explanation. And you can say some head only focus on and of and the period. And there's some research to explain why this behavior. You can search on Google, and you can also ask us. We will give you some paper to read. And finally, I want to introduce an advanced visualization tool. This is very powerful tool. This is BERT-VIS. This extends from the tensor to tensor visualization tool. And you can just copy this code to download the library, then import the library. Here, we use the head view here. So the head view requires 2 input, the attention weights. This is a list of tensor. And the input tokens. This is a list of tokens. So this should be the text token. You want to visualize that real text, right? And let's see, let's go to the layer 22nd. So here, well, you can say she refers to my daughter. And you can say this line between she and my and daughter. So the BERT model can realize this co-reference. It can find she refers to daughter. So I suggest you to use this tool. They also provide some different view like model view and neuron view. It will help you to investigate the behavior of the model to help you understand what knowledge did the model learn. And yeah, that's all about fine tuning BERT and visualization BERT. Any questions so far? No question? So Peter, are you here?
Hey, how's it going?
I'm good. How are you?
I'm good. I just finished the final.
Sure.
So I'm here to talk a little bit about the milestone 2. Let me see if I can forget how screen sharing. Oh no, I cannot share my screen. Okay. All right. So milestone 2 is building on basically milestone 1. So what we want is a progress report on how things are going. So you should have gotten feedback so far. Please look over it. Please discuss it with your group. There were some concerns with some groups in terms of maybe like the selection of their corpus or stuff like that. And if you have any questions about that, please please reach out to us. We sort of split up the feedback, so you can get more information on why that may have been a concern if you have any questions about that. But the basic idea of milestone 2 is you're going to take that feedback, sort of like update your project in terms of your plan of what you're doing. So some people may be changing their data or the models they're using. I know one thing that came up quite a bit is that like people were looking at using corpuses that were fairly small and using like some neural methods with those. And so you may consider using BERT, which is a pre-trained model, and it may work better on the smaller corpus if it's of the same genre that BERT's been pre-trained on. So, which is probably the case if it's standard English. So that may work better, and that may be something to consider if you got feedback on your corpus size, or if you're collecting data with your corpus. So you may change something like that. And so what we want is just to see you update your plan, take into those considerations, and then give a little bit more concrete detail on what you'll be doing. And you can actually start on your stuff as of now. So you can start like evaluating the models, start doing any of the engineering you need. If you are planning on collecting data from Twitter, I would apply for a Twitter developer, get that approval ASAP, and then start collecting. Collecting data doesn't take that long, but you need to note that it will take some time before you can start evaluating those results. So again, you'll take your milestone 1, and then you're going to update the data, what changed about it, any methods in engineering that may have changed, and what you're doing with those. So did you make any progress? Are those things still going to work out? previous works would be great to expand on. So this whole milestone 2 is sort of the earliest rough draft of your final project, and we're going to expect a like a background research portion of it. So for whatever model you're doing, make sure you're finding papers that sort of explain the model and show how they may be used in certain contexts, especially things that are related to the topic you're looking at. So say if you're looking at financial data, try and look at how other people are looking at financial data and what sort of methods they're using. For results, I don't know if anyone started running code. It would be good to start at least working on the engineering part of it. I don't think we're really expecting too much in terms of initial results for this benchmark, but if you have them early on, like if you're trying out a bunch of models and you have the code for those models already and you have the data, why not? That may be good, especially if you're trying to do something like fancy hyperparameter tuning and you may need time to go through all the grid search that you have planned. And challenges, definitely include this. So for challenges, so maybe you found that your data was not good. Maybe it wasn't annotated properly. Maybe the models that you're working on aren't working well, or you're having trouble getting them to run. Just make sure you update on us. That's a good way for us to know what support you need, and will allow us to sort of help address those challenges in office hours and when we talk to you on Slack. I think that's, yeah, and then the rest, yeah, rest of it is all the same. Yeah, are there any questions about how things are going? We're gonna break into sort of after tutorial office hours in a little bit, but are there any general questions on this benchmark? Can you guys hear me?
I can hear you.
Okay. Oh, here we go. Yes, perfect. So again, any questions? I'll give it a few minutes. And then we can sort of transition to do the same like group chat with your groups and then one of the TAs, if that was helpful. Was that helpful last time? Okay.
Yeah, we can use Slack waiting list to post your question.
Yeah, I think that worked pretty well last time. I was gonna assume that the Collab Ultra would be good, but Slack is actually very convenient for this. If there are no questions about milestone 2, I would suggest we then break into the after tutorial office hours. Triyu, how does that sound?
Yes.
All right, well, thanks guys, and we'll see you on Slack.
Sure. See you. Bye.